Welcome students to Mechpro classes. Myself Piraj Mojumdar. I welcome you to the third session of dynamic programming problem where we will have our knapsack problem. Okay. Now this knapsack problem I'll show you in two parts. The another one will be it is also known as 0-1 knapsack problem. Okay. So previously we have seen the introductory part of dynamic programming. Next we have the stagecoach problem. Now we are coming to the knapsack problem. And if you haven't seen the previous videos, I suggest you to watch the previous videos. Okay. Now, as you already know, you have the concept of dynamic programming as well. I can now directly go to the knapsack problem as well. Now, before going to the knapsack problem, I just want to give you a small introductory class, you can say, for greedy technique. That was a demand. Many of you actually was asking for the greedy technique or greedy algorithm actually. So I would like to give a brief, introductory class on greedy technique as well. Now, we already solved different problems. The previous stagecoach problem, we also applied greedy technique first, then we applied the dynamic programming problem to solve the same particular problem, and where we got the optimal solution by applying the dynamic programming. Okay, and the solution we got from this applying greedy technique was somehow not optimal, or you can say it was a bit larger than the solution that we obtained from dynamic programming. Okay, now this greedy technique, in short, I can tell you, it follows, you can say, or you can make a note, it follows local optimal choice of each stage with intention, you can say, of finding global optimum. Okay, so you can say greedy technique follows local optimal choice of each stage with intention of finding a global optimum. And second, you can say it depends on, it also find feasible solution, you can say feasible solution or selection, you can say. Okay, as we have to select the optimal route, so you can say selection as well. And third one, you can say we have to find the optimal solution. Okay, the optimal solution, you can say maybe minimum cost, or that is you greedy about cost. I already told you in the previous problem, stagecoach problem, while solving stagecoach problem, that greedy means we are greedy on cost, or you can say maximization of profit. So we are greedy about profit, you can say. Similarly, can calculate the minimum risk as well. Okay, so you can say we are greedy about risk. Okay, now coming to the application part, I can say the application many problem, knapsack as well, knapsack, job sequencing, you can say. Okay, sequencing of machines. Okay, so I can write job sequencing. Then comes minimum spanning tree. You also know what is spanning tree. I have given a video on spanning tree as well during network analysis module. So you can also apply greedy technique to find minimum spanning tree. Optimal, optimal march pattern, and you can say Huffman coding, and Dijkstra's, this is D, Dijkstra's algorithm for finding the smallest root. You also know, you also heard about the Dijkstra's algorithm, as I already solved the shortest root problem in network analysis. So you will know Dijkstra's algorithm and as well as minimum spanning tree. You also know job sequencing, and today we will be going to solve the knapsack, But this, optimal merge pattern or Huffman coding, they are mainly dealing with the, these things are mainly for, you can say, for the competitions guys as well, okay. So in our syllabus, we are having this knapsack problem under this dynamic programming. So let us solve this knapsack problem. First, we will know what knapsack is basically. Okay, what does this terminology knapsack means? You all know what a backpack is. A simple bag. A bag of, you can say, school bag or whatever, the hiker's bag, you can say. The bag somewhat, I can have a picture for better understanding. Sorry for my drawing is not so much good, but I can make you understand how the bag looks like. A hiker's bag, you can think of hiker's bag, or soldier's bag, you can also think. Okay, this has got these pockets, you can say. Okay, this has got nets, okay, as well. Now somewhat this kind it looks like. Okay, so this one is a design, and this one is a chain, you can see over here. So let me make a design for better understanding. Okay, so somewhat looks like, okay, you can see. So this is somewhat a knapsack, you can say. Okay, so a knapsack, you can say, a soldier's or hiker's bag, you can bag, you can say easily. Okay, so soldier's or hiker's bag, that is a knapsack, you can say, with shoulder straps also. Okay, you already know, you have already seen this type of bags. Okay, this generally carried on the back and typically made of canvas. Okay, so that is made of canvas or other weatherproof material also. Okay, now it can also be said as it is a case of canvas or leather, sometime of leather also, for carrying items on the bag as well. Okay, now this particular knapsack problem, you can say this knapsack problem is an optimization problem as well. Okay, so we are dealing with optimization. So this knapsack problem is a optimization problem used to illustrate both problem and solution as well, you can say. Okay, solution as well. Say we are given a set of items with specific weights and values as well. Okay, so we have got two parameters. One is your weights and second, say, values. Okay, the aim, our aim is to get as much as value into the next knapsack. This one is a knapsack as possible. So our aim is to get as much as value into the knapsack as possible, given the weight constraint, when weight is your constraint. Okay, you already know what is constraint. Okay, constraint of the knapsack. So this is the weight constraint of the knapsack, is this one, weight. Now in a knapsack problem, there is a knapsack with a total weight restriction, say W. Okay, now the knapsack is to be stocked. Okay, you can store item. Okay, so that is, you can also say as stacking. Okay, so the knapsack is to be stacked with items, with each item having a weight, say Wi, and a value, say Vi. I can be 1, 2, 3, 4, etc. Okay, so one can stack as many of any of the items in the knapsack. The problem is to find out how many of each type of items are to be, stacked. How many of the items is to be stacked into the knapsack so as to maximize the total value. Our objective is to maximize the, total value within the, this weight constant as well, or you can say the restriction. Now the formulation I can write it as I say this is the objective function as well. You can say maximize of z, and this is say n equal to sorry, it can be termed as I, say I equal to 1 to n. You can write vi into xi, okay, and it should be subject to a constant, say weight constant we are considering over here, that is summation of I equal to 1 to n and wi into xi, and that should be less than equal to the total weight or capacity of the knapsack, you can say, okay. And now one more thing you have to take consider, xi's are integers, okay. I can write it as integer, and xi is non-negativity constant, so xi should be greater than equal to 0, okay. Now one of the problem, I can say problem, not actually problem, difficulty you can say, or it is a simple one. The difficulty is that it is an integer linear programming problem, this one you can see, okay. So the solution needs special attention, okay. Let us now take a problem and get the solution. Now one more thing I forgot to tell you, we have to develop recursive relations. As I earlier told you, the parent of dynamic programming is recursive relationship. It also sometimes is known as recursive optimization. So we have to break a problem before applying dynamic problem. We have to break a problem into sub problems, or we have to find the stages. Then we have to develop a recursive relation as well, okay. So recursive relation for this particular knapsack problem can be written as g of iw equal to max vi plus g of iw minus I comma w minus wi and g of I minus 1 comma w as well, okay. Now this g iw is the optimum value of the knapsack of a combination of items, say 1 to I, okay. So this is the optimum value, you can say this is with cumulative weight of w or less, that should be w or less, okay. You should keep in mind. Now vi is the value, you can say value earned from a single type I item, okay. And you can say 0 if cannot be accumulated. You can say 0 for when we cannot accommodate, okay, that I can be 0. And wi also, this wi is the weight, I earlier told you, weight of a single type I item, okay. And vi plus this one, vi plus giw minus wi is the value of one number of the ith item, you can write, and plus optimum combination of weight, this one, optimum combination of weights from 1 to I, okay. And this one gi minus 1 of w is the value of optimal combination of weight. I can write it, this one, as the value of the optimal combination of weight w of items 1 to I minus 1, you can write, okay. So this is the recursive relation. Let us now see a problem, okay. Now we have a problem. The given problem has 3 objects and the corresponding profit and weights are given below for the 3 objects as well. For object 1 we have profit 25, for object 2 we have profit 24, for object 3 we have profit 15, and the corresponding weights of object 1 is 18, and weight of the object 2 is 15, and weight of the object 3 is 10 as well, okay. Now we have given a knapsack, there is a bag, say a bag, or you can say the knapsack is given, and its capacity is given as, you can say its capacity is given as say 20, okay. So its capacity is 20 as well, okay. Now we have to say, this is our bag, say we have to fill this bag and keeping in mind we have the constraint of the capacity as 20 as well. Okay, now we'll apply first, say we are greedy about profit. Okay, we are greedy about profit. So when we are greedy about profit, we'll see the profit. Our objective is to maximize the profit, so we'll see which one of the profit is highest, and corresponding weight will keep in this bag. Okay, so in this matrix you can see the profit of the first object is maximum, that is 25. So we will put that first object, say object 1, in this bag. So the weight of the first object is given as 18. So I can write it at, say this one is 18. I can write this one is 18. Say. Now the total capacity, we already know the total capacity is 20. So we have filled the bag with 18 capacity. So the remaining capacity is now only 2. Now for filling the knapsack with 18 capacity weight, we have got the profit of 25. As we are greedy about profit, so we will first consider the highest profit. Corresponding weight we have to fill in this particular bag. Now next we have got only 2 unit of capacity left, so we have to check the next larger profit among this matrix. Next larger matrix profit for this matrix is 24, and the corresponding weight is 15. So we have to choose this 15 weight. Now see, we have got only 2 unit of capacity left. We cannot fill 15, so we can fill a proportionate amount, that is 2 by 15 I can fill. As because we have got only 2 unit left, so we cannot fill this second object, as because 15 is the total weight. So we have to fill, or we can split that object in certain in this proportion, you can say 2 by 15 proportion, and accordingly we are getting the profit as well. So profit will be this one, 2 by 15 into 24. I think you have got this, and if you are having still a problem of how to find this proportionate one, you can comment in the comment section as well. So this will be coming around 28.2. Now let us consider, say we are greedy about weight. Okay, so I can write it, we can, the second approach will be, we are say greedy about weight. I can write, okay, in short form WT I can write. Now look, we have got the total capacity as 20. Okay, now we are greedy about weight, so we have to find the weight first. Okay, now look, we have got 18, 15 and 10. So we will look the minimum weight. Why? As because if we start from the minimum weight, we can fill as much as possible. If you fill the heavier one, then it will be much difficult to fill many items in this particular bag. So we will start from the minimum weight of the object. That will help us to accommodate many items as much as possible in this particular knapsack bag. So the minimum weight is given as 10 over in this particular matrix, and the corresponding object is 3. So we will fill with object 3. So say we have filled this object 3. So what we got? We got 10. So we got, say this is the 10. Okay, so you can say this is the 10. For filling this knapsack with initially with this particular weight, that is 10, we are getting corresponding profit as well. You can write this as profit. So we are getting profit equal to 15. Corresponding is 15. So you can write 15. Okay. Now 10 capacity is remaining. You can see total capacity is 20. So 10 capacity is remaining. Now we have to find the next lower weight, that is 15 is coming over. Now, as because we have got only 10 space left, 10 unit of capacity is left, so we cannot accommodate this directly in this item. So we have to accommodate a portion, or you can say in a proportion. Okay, so I can write it as 10 we have got remaining, and the next lower weight is 15, so I can write 10 by 15, and the corresponding profit is coming to 24. You can see from the matrix given over here. So we are getting 31 profit, you can say. Okay, so we are getting 31. So you can see when we are greedy about profit, we are getting 28.2, and when we are greedy about weight, we are getting profit as 31. Now another option available is the profit by weight ratio. I will find the profit by weight ratio as well. Let us see. We are having, I can write it as well, profit by weight ratio. I can write, okay, profit by weight ratio. So you see, for object 1, so this can also be termed as greedy about both. You can write greedy about both, you can write, okay, that is profit and weight as well. So you can write greedy about both. Now for object 1, object 2 and object 3, we are getting the profit by weight ratio. Profit by weight ratio 25 by 18, 1.3 for 1, and for 2, 24 by 15, 1.6, and for 3, 15 by 10, that is 1.5. Now you can see we are having the maximum one is 1.6. As we are greedy about both, we have to consider this one, that is the object 2 we have to fill first. So we will fill the object 2. So I can write object 2. Now the total capacity is how much? 20. So object 2 is having weight 15. So we are only having 5 unit of capacity left. You can see as well. So it is very clear. Now if you calculate the profit for this particular case, we are having first object 2. You can see object 2 we are having profit how much? 24 I can write. Next we are having only 5 unit left. So in proportion we have to fill this, as because this weight is 15, total weight is 15. So I can write we have to consider that we have already taken the profit as 24. Now we have to consider the next higher value. The next higher value is 1.5. Okay, so next higher value is 1, as because it is 1.5 we have to consider this object, filling up this object. Now look, this object has got 10 value, 10 capacity of weight. Now but we are having 5 capacity of weight only, so we have to fill in a proportion. That is we have to split this particular object 3 and we have to put this one. Okay, so in order to put this object in this knapsack, we have to make a proportion. Say we are having 10 weight, but our capacity is limited to 5 only, so we have to make a proportion, and the corresponding profit is 15 as well. Okay, so I can write it as this one. So we are getting a profit of 31.5. Now you can see in this particular knapsack problem, when we are greedy about profit, we are getting 28.2. When we are greedy about weight, we are getting 31. But when we are greedy about both, that is weight as well as profit, we are getting the highest value. So you can say this is the optimal value. Okay, so for this particular knapsack problem, we are having maximum weight value, or the optimum value is coming to be 31.5. Okay, now we will see 0-1 knapsack problem as well. Now let us consider another form of this particular problem. You can say it as a 0-1 knapsack problem. Okay, what does this 0-1 knapsack problem? In binary coding, 0 means nothing and 1 means positive 1. Okay, that is we are having something, a value. Okay, so 0 is null, you can say. Okay, so this 0-1 knapsack problem says either you fill the whole object or not at all, you can say. So this is 0, 1 knapsack problem. Now let us see with a problem. You say, now look, say we have object say 1, 2 and 3. Now the profit of this corresponding, you can say, is say 20, 25 and 60, and the weight, say we are having 2, 4 and 8, say. Okay, now let us consider a knapsack. We are given of some capacity, say we are given a capacity of, say, knapsack capacity, I can write it over here. Knapsack capacity, you can write as, say, maximum capacity is given as, say, m equal to 12. So that is the maximum capacity. So we have to fill this knapsack in such a way with this particular objects 1, 2, 3, so that we will have a optimal solution, or you can say maximum profit, you can say. Okay, so this is our aim of knapsack problem, to obtain the maximum profit. Now let us solve. Say let us find the profit by weight ratio. So for this one we are having 10, this one we are having 6.2, and this one we are having 7.5. Okay, now we have this, knapsack, say this is the knapsack. Okay, now look, the maximum value is this one, corresponding object is 1. So we'll fill this with object 1 first. Object 1. Okay, now for this object 1, the weight is is 2 only, so I can write it as 2. The total capacity is 12, that is given to us. Okay, now 10 is remaining. The next higher value, first one is this one, the next higher value is this one, 7.5. The corresponding object is 3 and the weight is 8, so I can fill it like this. So this becomes 8. Now the object is 3 as well. So for first object we are having profit, how much? Profit is 20, so I can write profit equal to 20, plus for third object we are having profit is 60. Now 8 plus 2, that is 10, we already have got. Now remaining is only 2 unit of capacity. Okay, but you can see the next item, we already filled this one and this one. In this we have put this object 1 and object 3 in this knapsack. Now we have remaining only this object. Okay, but this object's weight is 4, but we are having only 2 quantity of capacity left. Say, look, this is 0, 1 knapsack problem. This is not like the previous one. We can fill it like in a proportional way. So either you fill or not at all. So we cannot fill with this one, as we cannot allow to split the object. So our maximum profit will be coming around 60 plus 20, that is 80. But you can say, you can ask yourself, is this the optimal solution? Is there any another alternative? Let us see. Look here, for each and every object, I can say 1, 2, 3, 4 up to n. For each and every object we are having probability of 50%. That is, we are having 2 choices for each and every particle. Either you fill it up or not at all. So possibility I can write 2 to the power n is the possibility I can write. Okay, now look, how many items are there? 3 items out there. So for this particular problem we are having possibility of 2 to the power 3, that is 8. Now out of 8 only 1 will be the optimal solution. 1 will be your optimal one. Okay, now we have to find 8 ways, and we have to find the optimal out of that 8 ways. Okay, now let us have some basics of computer science, you can say. In binary coding we can write this in the form of 0 0 0, first condition. Okay, second is 0 0 1, third is 0 1 0, you can write, and fourth one is 0 1 1, fifth one is 1 0 0, you can write. Okay, next is 1 0 1, you can write 1 1 0 and 1 1 1. So those who are having a little bit of concept of binary can easily understand this coding or algorithm, you can say. Okay, now for this first case, if you consider the first case 0 0 0, that means we are not putting any of the object in the knapsack. So this is the knapsack, we are not putting any of this, so we can say we are having no profit, you can say. Okay, for this first case, that is gone, this case is gone. Now for this case, we are putting only object 1, sorry, this is the 3, that is the object this one, so we are having profit of, you can say, 60. Okay, now for this case we are putting object 2, so we are getting profit of 25, you can say. For this case we are putting object 2 and 3, you can see, I can write 1 2 3, so object 2 and 3 we are putting 2 and 3, so profit will be 85. Now for this case we are putting object 1 only, so the profit will be 20 as well. For this case 1 and 3, that is 20 plus 60, that is 80, you can say. For this case 1 and 2 I am putting, so 20 plus 25, I can say 20 plus 25, that gives you 45 as well. Now for this one 1 1 1, look, if we put 1 plus 1 plus 1, how much will be the weight? Summation of 2 plus 4 plus 8, 4 plus 2, that is 6 plus 8, 14. But our capacity is 12. We cannot fill all the object at a time. So this is also a no profit condition, you can say. Now out of this, how much? 1 2 3 4 5 6 7 8. So out of this 8, the optimal solution is this one. So the value is 85. Previously, how much we got? We got 80 by applying greedy for both method. That is greedy for profit as well as weight. So we calculated using greedy method and we find the value is coming to be 80. But you can see in hit and trial method, direct method, you can see we are finding the optimal solution is coming to be 85 for this particular 0 1. This is a special type of a knapsack problem, you can say. The problem and the optimal solution or the value is coming to be 85 as well. Now I think the knapsack problem is I think you are very much confident about solving knapsack problem in your semester examinations, and if you are having any problem as well, you can always comment me in the comment section. Hope you have enjoyed the session. Thank you for watching.